Okay, I don't know what happened, but I believe we are streaming. Okay, though, so shall we begin?
Sure.
Uh,
Yes.
okay, so it's a great pleasure to welcome Seamus Albion from the University of Vienna, and he will be speaking on an elliptic An-Selberg integral.
Okay. Thank you very much, Gaurav, for the introduction, and thank you for the invitation to give a talk in this seminar. So I'm going to talk about kind of a paper that recently appeared on Archive with Eric Rains and Ola Varner, where we prove an elliptic analog of the An-Selberg integral. And so my goal is for the first part of the talk will be to tell you what on earth an An-Selberg integral is, and then after that, I will move on to well, I'll hopefully try and explain the elliptic side of things in a bit more detail. And then, yeah, at the end, you'll hopefully see how all of this fits together. So I'm going to begin by telling a story, which I'm sure many of you have heard before, but like any good story, it's worth retelling, especially when it's the subject of your talk. So my talk is about a generalization of the Selberg integral. So what is that? So in 1944, Atle Selberg, who you can see here, he published a multivariate analog of the beta integral, which is now known as the Selberg integral. And you can see here, it's really if you can see my cursor, it's an integral over the unit cube, k-dimensional unit cube, as I've written it here, where you take k times the ordinary beta integral density or beta function density, but you pair it with this Vandermonde determinant or Vandermonde product type thing raised to the power 2 gamma. So you have a third complex parameter gamma now. And his observation was this still evaluates in a nice closed form, as in particular as a product of gamma functions. And that's what I mean by a nice closed form. And here you should take alpha and beta and gamma complex numbers such that the real part of alpha and the real part of beta are positive. That's inherited from the beta integral. But the real part of gamma satisfies now this kind of more complicated condition, but you should think about it as it's allowed to be slightly negative. You can see that by actually analyzing the right-hand side, the numerator of the right-hand side. And so Selberg gave a proof of this, and his proof is really nice. I encourage you to read it. The paper is written in Norwegian. I'm sure not many of us here speak Norwegian, but you can find versions of it, for instance, in the book of Meta on random matrices, and it's also outlined in a great review article on the Selberg integral by Peter Forrester and Ola Varner, which I will explicitly reference later. So I said that the Selberg integral was published in 1944, and that's true, but it actually first appeared in print in 1941 in a different paper of Selberg, where he was trying to prove some kind of property of analytic functions. And so he didn't believe the integral was new, which was kind of one of his main hesitance behind publishing a proof of it until 1944. And so actually what really happened was that Selberg, he has a footnote in this paper where he says, I don't believe this formula is new, and if it is, well, I'll publish a proof later. And in 1944, he was asked to publish or contribute something to a journal, a Norwegian journal, which was primarily read by mathematics teachers. So he thought it would be a good opportunity to publish a proof of this integral formula. And it's actually his only paper written in his native language of Norwegian, published paper. The rest are in German or English, I believe. And so there was this 35-year period where no one really knew about the Selberg integral except Selberg and I guess a handful of Norwegian mathematicians, but there were some other people, and I haven't written their names down. But if you go on MathCNet or MathSciNet, I should say, you can find this one citation, and they apply the Selberg integral with alpha equals beta equals 1, and gamma equals 2. So if we go back to the previous slide, that's really just evaluating the fourth power of the Vandermonde determinant over the unit cube, which I don't know. You probably didn't need the Selberg integral before. If you work hard enough, I think you can do that completely directly. in any case. So what happened in 1979? Well, between 1944 and 1979, people in random matrix theory, so Mehta and Dyson here, where they conjectured this integral formula. So I've written it here as the Mehta integral, and this is very much no longer a conjecture, but they could evaluate this for 3 values of gamma. So they could evaluate it when gamma is, I think, 1/2, 1, and 2. And then they could also evaluate it when k, for arbitrary gamma, when k is small, so maybe 2 and 3, I think, or maybe even just 2. And they conjectured this general formula, but no one was able to prove it. And in fact, Mehta publicized it a lot. So in here, the first edition of his book on random matrices from the 60s, he includes it as a conjecture. And then he also published it in the problems of the Siam Review as an open problem. So people started to refer to this as the Mehta integral. And all you've done really is you've kind of taken an exponential type limit, which you can do also for the beta integral to obtain the definition of the gamma function. But in this case, it actually produces a novel integral formula, but you still have this nice Vandermonde to the 2 gamma. And you can see actually this part of the evaluation was already in the Selberg integral. So what happened in 1979, really, I said I would tell you that before, but now I'm actually going to tell you, was that Enrico Bombieri, who was also at the Institute for Advanced Study in Princeton with Dyson, with Selberg, he discovered an integral that looked very similar to the Selberg integral. And a colleague of his, explained to him that it was related to some work of Dyson. So he went and spoke to Dyson, and Dyson told him about the Mehta integral. And then he went to Selberg because Selberg was the preeminent number theorist, and he wanted to ask him his opinion on his work. And Selberg said, well, this integral looks something like I did 30 years ago or so. And he gave him an off-print of the paper in Norwegian. And then Bombieri says that he deduced that he immediately saw you could evaluate this Mehta integral, or Dyson Mehta conjecture as it was then, using the Selberg integral. And so all of this is outlined. Oh, sorry. Okay, so I got a bit confused there. So I'm actually going to tell you where the Selberg integral has appeared, and then I'll tell you what I wanted to say just then. So the Selberg integral, it's kind of, after this rediscovery, has kind of appeared almost constantly since 1980, so in the last 45 years or so. So it starts out in random matrix theory with the Dyson and Mehta's original motivation. So this was to do with kind of, it's related to constant terms. And so what I wanted to say about Dyson and Mehta's original motivation was really that this was to do, Dyson was in the process of writing a very long series of papers called on the energy levels of complex systems, or statistical theory of energy levels of complex systems. And in this, he also conjectured a constant term identity, which was very, very quickly proved. But there were kind of generalizations of this constant term conjecture and the Mehta integral, which was still a conjecture, by MacDonald. And this kind of added to the appearance of the Selberg integral in the literature. And after the rediscovery by Bombieri, people really quickly realized that you could use the Selberg integral to prove a lot of these MacDonald conjectures. Another thing is that it appears in analytic number theory, kind of in a kind of funny way, which is through this Keating-Snaith hypothesis, which conjectures a relationship between the moments of the Riemann zeta function and the distribution of those moments and the distribution of eigenvalues of large random matrices, which is where the Selberg integral comes into play. It also appears kind of in combinatorics. So in Stanley's, the second edition, I think, of Enumerative Combinatorics Volume 1, Stanley gives a combinatorial interpretation of the Selberg integral, but also related to Q integrals. So people like Jung-Soo Kim and Dennis Stanton and Sejin Oh and Jung-Soo Kim have looked at things like this. So from the Q integral, the Q Selberg integral from this point of view. And then kind of what's related to what I'm talking about today is conformal field theory. So there's a system of partial differential equations, which you can place on any Lie algebra called the Konechnik-Zamolodchikov equations. And the Selberg integral arises for SL2 as a really, really special case of the solution to these equations. And that inspired a lot of what I'm going to talk about now. Okay. And so if you want to read more about this, which is what I wanted to say before, you can read this really nice review article by Peter Forrester and Ola Wagner, which is 15 years old now. But they go really over all of these things that I've just mentioned and all of the history of the Selberg integral. You can see a letter in Selberg's handwriting that he wrote to Dyson about integrals like this. You can see Bombieri actually explains what happened with the rediscovery of the Selberg integral in his own words. So it's really nice. Okay. So I promised I want to tell you about AN Selberg integrals. So as I already said, you have this Vandermonde product in the integrand of the Selberg integral. And if you know anything about root systems, you know that the Vandermonde product is really the evaluation of the Weyl denominator in type A. So when you have n k variables, as I do here, this will be type AK. And that's not the point of view that I want to take. I want to take a different point of view. And I really want to think about the Selberg integral as being an A1 or an SL2 object. And you won't really need to know anything about root systems for the rest of this talk. All I'm going to use is the Dynkin diagram of type A, and I'll allude to other types. But so how do I do this? Well, I take the Dynkin diagram and I weight the single vertex as follows. So I associate my integer k, my two complex parameters alpha and beta, with this vertex. And then I define the weight of this vertex to really just be the integrand of the Selberg integral. And so now I'm going to start using these deltas. So there's a lot of deltas in this talk, but this is the first example of a delta. Okay. Okay. So I've told you what A1 is. That's just the Selberg integral. But what about A2? Well, so for A2, things get a little bit more complicated. So now I have a pair of integers. So each vertex is going to get an integer, but I need to impose an ordering on the integers. So one needs to be larger than the other. And I'm choosing that the rightmost vertex in the general picture, but on the vertex on the right here is going to carry the larger integer. And moreover, each vertex is associated with its own set of variables. So I have now two sets of variables. Okay. And these sets of variables need to interact somehow. Why? Well, because in the Dynkin diagram, there's an edge between the vertices. So that's that's not a very good reason at this stage, but there's more of a reason. So how they are paired precisely is through this kind of what I'm calling an edge weight, or this kind of edge Vandermonde product, which depends on now on two independent sets of variables, and it pairs them like so. And the weight of an edge will be, you take this Vandermonde type product, take the absolute value, and you raise it to the power minus gamma. And there's one other thing which I'm kind of, which I haven't mentioned yet, which is that I only have a single beta, but I'm allowed to keep two. I'm allowed to have two alphas, but I'm only allowed to keep one beta. Okay. And there is a reason for this, and I'll explain the reason a bit later. But
I have a question.
Yeah.
So this sort of an inversion almost seems like a Cauchy formula in the making, and the Cauchy identity. I mean, is it almost going? I mean, like summing over sure characters of X and sure characters of with regards to Y.
Yeah. I will mention this later, but the Selberg integral is related to a Cauchy type identity. That's definitely the case. But this edge weight is, it looks a bit Cauchy-like, but it arises for a slightly different reason than the appearance of the Cauchy identity. But the Cauchy identity is really hiding behind all of what I'm talking about.
Okay.
Thanks. Okay. Yeah. So, okay. So now I've given you the recipe. I should give you the integral. So here's the Dynkin diagram. We'll keep it hanging around. And so in 2003, Tarasov and Vachenko, they evaluated the first instance of a higher rank Selberg integral, which I'm calling the A2 Selberg integral. And so, as I said, you only have a single beta, which is attached to this second vertex. This second vertex is carrying the alphabet Y. And I take the absolute value of a product of two Vandermonde determinants raised to the 2 gamma. And then this evaluates nicely. Okay. Okay, you might think this is not nice. And if you don't think this is nice, then you should probably not watch the rest of the talk, because this the smallest, the formula is going to get bigger from here. But in any case, one thing you can observe immediately by looking at this right-hand side, okay, is the following. So if you, okay, so I mean, so the domain of integration, I've written it here, but it's no longer as nice as it was before. So it's not just some kind of K1 plus K2 dimensional unit cube. You need to be careful, really careful with what the domain is. And it's a chain in the sense of, in the algebraic topology sense of the word chain. So what that means is that essentially you're kind of carving out a path through this kind of very big unit cube, but it's really a weighted sum of smaller integrals. And the weights, you can compute them explicitly. They're products of sine functions, but there are weights. There are weights involved. So kind of that the notation kind of obfuscates a bit of that complexity there. But one important thing is that if you set K1 is 0, then the integral actually collapses just to the ordinary Selberg integral. And the domain here collapses to the K simplex. Okay, and you might say that's not the original domain of integration. And while that's correct, the integrand of the Selberg integral. So let me go all the way back. If you look at the integrand of the Selberg integral, it's symmetric. So if you take this integrand and you integrate it just over this simplex, if you symmetrize the domain of integration, so you take any permutation of these variables, the value of the integral is going to remain the same. So all you have to do is multiply the value of that integral you get here, taking over the simplex by K2, in this case factorial, and you can play with gamma functions and absorb these K factorials. But you're really just going to get back the Selberg integral. And you can actually see that immediately from the evaluation, because if you set K1 is 0, the first two products here just disappear, and you only have this product over up to K2 here. And this is just the value of this. This is just the value of the Selberg integral, as I said, after you've played with these gamma functions on the right. With A1 vanished, A1's gone, and you just have A2. The other thing is that I didn't say anything about the parameters, okay? So the parameters, alpha 1, alpha 2, beta, and gamma, so they're still complex numbers, but the conditions get more complicated. There is some domain of convergence, but now gamma has to be, I said before that gamma could be a bit negative. Gamma can still be a little bit negative, but it also has to be small. It can't be very, so as K2 gets bigger, the real part of gamma has to remain smaller. Of course, when K1 is 0, you can get rid of this condition. And really, actually, this condition, you can see it explicitly on the right-hand side. It comes from this gamma function here. Okay, anyway. Okay, so for type AN, there's really nothing more to do. Everything's really already in the picture. You just kind of add more copies of this rightmost vertex. So now you have a set of integers K1 through Kn with some ordering on them. So you can kind of think about this as a partition, of course, written backwards. I have now n alphas and only a single beta, which lives on the rightmost vertex. And in 2009, Olavana evaluated this AN Selberg integral. And here it is. The generalization is kind of exactly as you would expect. Now you have n-1 edges, so you have n-1 edge Vandermonde products. If you know some theory of Lie algebras or things like that, you'll observe that the coefficients of gamma in these powers are really the entries of the Katam matrix. And that in general will be the case. So if you want to write down a Selberg integral for the Lie algebra, simple Lie algebra G, you can do that based entirely on information coming from the Dinkin diagram. And the conjecture...
Sorry, could you repeat that? Which part is coming from the Katam matrix?
The coefficient of gamma. So here you have a 2 gamma associated to a vertex. It's the inner product of a simple root with itself. And then these, the product of alpha 1 and alpha 2 is going to give you -1. So that's where you get this from. So these edges represent you have this -1, and the vertices give you the 2s.
Because you're saying the coefficients of these gammas, they are coming from the Katha matrix, fine.
Yes.
One more thing. I mean, here you're taking K1 less than equals to K2 like that. So is this like something coming from the dominant Weil chamber for the weight or something like
Yeah,
that?
exactly. So what's really hiding behind this is that you have a tensor product of 2 highest weight modules for, say, in a Hewlett type AN, so SLM +1. And you essentially want this tensor product, when you expand it in terms of reducibles, to be multiplicity free. And so that's actually also why you only have a single
basically,
beta.
you're saying that you're working with some place where the Littlewood Richardson coefficient is just coming out to be 1 sort of a thing.
Yes. And that's really so I didn't write the conjecture down explicitly on the slides because I kind of wanted to slide it under the rug, but there is a conjecture of Mukhin and Vachenko which says that modulo some representation theoretic condition, which kind of looks like what I just explained, so that you want some multiplicities all to be 1, essentially. Then when you integrate some what they call the master function, which kind of is the integrand of the Selberg integral for AN, for example, but for arbitrary types, it looks a bit different. Then this should evaluate as a product of gamma functions. And that's essentially all the conjecture states. They don't tell you the domain of integration or what the product of gamma functions should be. So kind of just, yeah. But it's...
I mean, the domain, I can imagine how it should come out to be for the general one, because it was something while we are having an action by the Weil group on the unit simplex sort of a thing, right? Unit cube sort of a thing, and one is having an action of the Weil group. Isn't that how the simplex is coming? Because I mean, the example which you gave over there, C gamma, that was like 0 less than equals to, 0 less than y1 less than y2 less than yk less than 1. That's almost like I can imagine it to be like the coordinates still 1, and then we are making a rectangular pyramid over this sort of a thing.
Yeah, so I'm not exactly sure. So the way the domain arises when you're actually doing when you're in the proof is that you essentially you need this product you're getting here to not blow up. And so the domain is tuned in a way to make that happen. It could be that there's a nicer description in terms of what you're saying, but I don't know it. That's maybe what I should say.
Okay, fine. I'll look up to that. Thanks.
Yeah. Anyway, so here's the evaluation. As I said before, that I've written it here with beta r, but all the betas are 1, so that this doesn't exist, and you just have a single beta sitting on the end vertex. Okay, and so as I said, as I gave before, if you set K1 as 0, here this reduces to a type A n-1 integral, just like when we passed from A2 to A1. And I should say something about the proof. So we've already mentioned the Cauchy identity, but the Cauchy identity for Macdonald polynomials is really what hides behind the proof of which gives one proof of the Selberg integral. And so Vienna used these kind of AN type Cauchy identities, to prove the AN Selberg integral. So it arises after taking an appropriate limit. And the advantage of using the Macdonald polynomial approach, which is different to Tarasov and Vachenko. Tarasov and Vachenko really used a representation theoretic approach when they were evaluating the integral. So the Macdonald polynomial approach has a big advantage, which it allows you to include symmetric functions in the integrand of the Selberg integral. So in type A1, this was done by Cadell, again, not using Macdonald polynomial theory kind of explicitly. And then type AN by Wagner. And type A1, you can actually get a pair. So this is much more recent. So Cadell did this in the 80s. Wagner is 2009. So around 2012, Albafateev, Litvinov, and Tanopolsky, they realized you could include 2 Jack polynomials in the integrand of the ordinary Selberg integral, but with some platistic shift. And then a few years ago, in a precursor to what I'm talking about today, myself, Eric Rains, and Olivana, we generalized this to AN. So we included a pair of Jack polynomials in the integrand of the AN Selberg integral. And I'll say a bit more about generalizations involving symmetric functions later on. Okay. So now I've told you about the classical stuff. Let's talk about the elliptic stuff. So the goal of this section is to just tell you what the elliptic version of everything I've just explained to you is. I need some elliptic recipe. So I've given you the classical recipe for the AN Selberg integral. Now I need to give you the elliptic recipe. Okay. So this is all based on kind of the theory of elliptic hypergeometric functions. So we have the elliptic gamma function. So this was defined by Roysenaz in the 90s, and it has a slightly simpler definition than the usual definition of the gamma function you're given, which is just this nice infinite product. But you can automatically see from this that it's always going to have zeros whenever you take z to be a p times q and the exponents are positive integers. Any pair of positive integers, that's going to give you a zero of this function. And it's going to have poles precisely when p and q the exponents are any pair of non-positive integers. It also has an essential singularity at the origin, because you can see that this this 1 minus 1 over z, essentially, the pq over z kind of thing, appears in every term in the product. And there's many nice formulas for this function, but one of them is one of the nicest is the reflection formula. So you just take z and then pq over z, and the product of those two is going to give you 1. Of course, this will never work when z is when z equals pq to integer powers. But that's, of course, still like the classical reflection formula for the classical gamma function, which also has to avoid integer points. And I'm going to use this plus minus shorthand notation forever now. Okay. So in 2000, Spiridonov evaluated the elliptic beta integral. So here I have 6 parameters. I have t1 through t6, and then I have a p and a q and a t. So I really have 9 parameters in total. And it's just this integral over the unit circle of, you take these gamma functions of tr z plus minus, and then there's some plus minus squared in the denominator. And this equals a nice product of elliptic gamma functions. But you have to the parameters have to satisfy the balancing condition. So the product of the TRs, T1 through T6, has to be P times Q. Okay. And if this looks a bit funny to you, you should think about the Barnes beta integral. So this is a classical result. So these are ordinary gamma functions now. And this is kind of the prototype for the elliptic business. So you take an integral of gamma functions, and that gives you a product of gamma functions again. And here the contour should be such that the poles which go to minus infinity as you increase n. So the sequences of poles depending on parameterized by integers, and the ones that go to minus infinity should be separated from the ones that go to plus infinity. That's what this contour from minus I infinity to I infinity is doing. And you can actually deform the contour of the elliptic beta integral to not be the unit circle, provided you ensure that these, and also, I should say, by doing that, you can remove this restriction that all of these TIs lie inside the unit circle. But your contour still has to separate sequences of poles which go to 0 from those going to infinity. Okay, so now I'm going to adopt the exact same point of view I had before, but I'm going to work with at the elliptic level. And I just want to stick all my parameters on this single vertex. So I stick my parameter k and my six complex parameters t1 through t6. You should think about p, q, and t as kind of living off the Dinkin diagram. You always have to have them at the elliptic level. So, and the vertex weight now, I'm just going to define it as the weight of the elliptic Selberg integral, which is defined here. So you can see that I now have this Vandermonde type product. And this you should think about as the Vandermonde product, the analog of this Vandermonde to the 2 gamma. So what's gamma? So you should think about gamma as T. So T without an index. That's really where gamma has gone. And then here is what's carrying the parameters. And I've defined this for an arbitrary set of parameters, T1 through Tm, but I'm only going to use it when m is 4 or 6. Okay, so I also have this funny prefactor, which is just the k deformation of the prefactor I had before. And then I have some more general plus minus notation. So if I have a player of things with plus minus, then I take all possible combinations. So AZW, A W over Z, and so forth. And that's what I'm using in this Vandermonde product here. And really, this is just to ensure that everything is symmetric under permutation and inversion of the variables. The integrand of the Selberg integral was invariant under permutation of the variables. Integrand of the elliptic beta integral was invariant under Z is replaced by 1 over Z, as you can see here. And now the integrand of the elliptic Selberg integral is kind of, you put these two things together. So you get what's generally called BCN symmetric. Okay. So the elliptic Selberg integral, or what I'm calling the elliptic Selberg integral, was conjectured by Van Dien and Spiridonov, and it was proved by Eric Rains. And it's this simple formula here. So you take a k-dimensional, an integral over the k-dimensional product of k unit circles, and this equals some nice product of elliptic gamma functions. And now you have a slightly more general balancing condition, which depends on k, but again, you have to have this, you can deform the contours if you like, if you want these parameters to not be inside the unit circle and all of this business. So it's kind of the same. So, not only did Eric prove this, but I think in a different paper, actually, he showed that you can, if you take a really clever limit of this integral, you actually get back the Selberg integral. So really the Selberg integral is contained in this. And there's one thing that kind of makes this funny, which is that I'm talking about I'm going to talk about an AN analog of this in a bit. But this integral here is often called the type 2 CN elliptic beta integral. And this comes from a slightly different naming convention of Van Dien and Spiridonov. Yeah. So if you see this integral and it's called the type CN, I guess I would be CK here because I have a K, or type 2 CK integral, that's Y. It's just different naming conventions. But as I said before here, I'm kind of taking a different point of view. So now the rank of the Lie algebra is not the number of variables, it's something else. Okay, and there's only one thing left to tell you before I can write down the AN elliptic Selberg integral for you, and that's the edge weight. So the edge weight here is it's a, I don't know, it looks kind of a bit funny, but it's this kind of it's again it's always going to be a product of gamma functions, but it depends on this kind of C parameter, which is the square root of PQ over T. So you have to pick a branch of the square root here, but that's beside the point. And this will be the edge weight. And this is kind of a funny thing because it appears actually frequently in the literature already, but kind of to do with these kind of Van Dien difference operators. So it satisfies some kind of like nice properties with respect to these difference operators, but here it just appears, and there's a reason it appears, which I'll tell you later on. Yeah. Anyway. Okay. So here's the integrand. I haven't given you the evaluation, but here's just the integrand of the elliptic Selberg integral, and I'm putting it all in this notation. So I have n sets of variables. I have T1 through T2n plus 4. So I have 2n plus 4 parameters, T, but I also have a T, P, and a Q. Remember, C isn't really a free parameter. It's the square root of PQ over T. But I've written question marks here because it's not really obvious what the parameters sitting on these vertices should be. And it's what you see here actually is that, so the last vertex carries 6 parameters, as you would hope. But all the other vertices carry, well, they carry two parameters associated with that vertex. So here, the first vertex would carry T1, T2, multiplied by some C, but that's beside the point. So the first vertex would carry T1, T2, and the second T2, T3. But T1 also needs somehow to see the reciprocals of T2 and T3. Okay, and why is that? Well, remember, for the AN Selberg integral, for the non-elliptic case, I had that beta R was 1 when R was less than N. And that's the manifestation of this at this level. So this kind of restriction is still arising. You should think about, I would hope here, in a general case, if I could have arbitrary betas and arbitrary alphas, then I would have 4 parameters associated to each vertex. But that seems to be too much. And so you can only have 2 free parameters and 2 which are restricted. So here's the kind of the main result, which is the AN elliptic Selberg integral. So each vertex as well, something I didn't mention on the previous slide because I wasn't stating the integral evaluation, each vertex has to carry a kind of a balancing condition in and of itself. And the balancing condition always involves these last 4 parameters. Okay. And as before, I've always got K0 is always 0 and Kn plus 1 is always 0. So that's how you should read this. And then if I integrate this big density I showed you on the previous slide, I get a nice product of gamma functions. And this is really a nice, I would say this is really a nice product. Okay. And this completely generalizes structurally the AN Selberg integral of Varma. So the structure is almost completely identical. In particular, for n equals 1, we get back the elliptic Selberg integral of Van Dien, Spiridonov, and Reins. The domain of integration now, well, because we're working with contour integrals, things are a bit nicer. They're like the AN Selberg integral, you can write it as a contour integral, if you like, and that's a bit nicer. The only reason we have this complicated domain of integration is because we want to keep a real domain rather than passing to a contour integral. But here the structure of the domain of integration, the contour it has this nice product structure. And in the paper, we explicitly give all the points which need to live inside the contour and things like this. So the contours are really explicitly defined. And the proof technique, which I'm going to outline now, uses this elliptic interpolation kernel of Eric Reins, which I alluded to in the abstract of my talk. And one advantage of this is this elliptic interpolation kernel kind of analytically continues what are already known generalizations of the McDonald polynomials and the Jack polynomials. And so we also obtain generalizations involving BCN symmetric functions, which generalize the Cadell and the AFLT integrals, which I was talking about earlier. Another interesting thing that happens at the elliptic level is that if all the Ks are equal, so remember I had this the first vertex was less than or equal to the second vertex, the number of variables and so forth. If you have the same number of variables at each vertex, all these Ks are equal, then there's an integral of Van der Bolt, which essentially does it all for you. And you can integrate out essentially the first set of variables, and this isn't really true for the non-elliptic AN Selberg integral. So this allows you to give a really simple proof with the initial only relies on the fact that the initial condition is the elliptic Selberg integral. So that's quite nice. But there's some bad news. The bad news is that at the moment, we don't really know how to take a nice limit of this integral we have, this kind of big expression, and obtain anything to do with the AN Selberg integral, even a nice Q analog of any kind of Selberg type integral. So it seems that at the moment, this is really just a structural generalization. The relationship with the known formulas is not so clear. And it's something that would be really interesting to know. So how does this relate to the ordinary AN Selberg integral? Since we already know that the elliptic Selberg integral kind of sits above the ordinary Selberg integral, of course, in a complicated way, but still. And now I want to talk about kind of the proof technique. So, as I said, the proof uses this thing called the elliptic interpolation kernel. So this was a tool that Eric Rains kind of invented or came up with to prove. He had a lot of conjectured integral transformations for elliptic hypergeometric integrals, and he wanted to prove these. So he introduced this kernel. And so it depends on two sets of variables of the same length. Okay. And you can define it essentially by a branching rule. So, so there's an expression for the kernel with two sets of n variables in terms of the kernel with two sets of n-1 variables. And you can choose the initial condition as well. So you can either take that the kernel with no alphabets is 1, or that the kernel with a single alphabet is this nice product here, which should look familiar. It kind of almost looks like this edge product I had, but there's some fudge factor at the bottom just to make things nice. And here I should say that C is no longer PQ over T to the 1/2. C is arbitrary non-zero complex number. Okay. It also has some really remarkable symmetries, this kernel. So I haven't given you the official definition, and I won't give you the rigorous definition, but it has some kind of fun symmetry. So if you can swap the alphabets X and Y, it's symmetric under swapping these two alphabets. And moreover, it's symmetric in P and Q, which is what you would hope. Okay, and so what is this interpolation kernel, this funny object? Well, if you restrict so that C squared is some T to the n-1 AB, and you specialize this one of the alphabets as this kind of progression. So this bold lambda is what's called a bipartition, which is just a pair of partitions, lambda 1, lambda 2. And if you take this specialization of the second alphabet here, I've written about either alphabet, then this kernel becomes an elliptic interpolation function, also due to Rains, times some product, some factor. Okay, and you can see here kind of T is hanging, the C is hanging around, and C squared and so forth. Anyway, and these elliptic interpolation functions, they generalize. I mean, if you want to push everything away, you want to get rid of all the parameters, all the BCN symmetry and everything, you go all the way back down, you really get Schur functions, but you can get Macdonald polynomials, non-symmetric Macdonald polynomials, things like this out of these functions. So they're really quite general. And the kernel is really an analytic continuation of this. So you should think about it as, well, I have a function, this interpolation function. It depends on a set of variables X and then a partition. What if I say that I want it to depend on a set of variables and not a partition of integers, but a partition where the entries are just arbitrary complex numbers? That's essentially what this kernel is. And kind of one of the key results that we use is that if you take this kernel and you integrate it against the Selberg density, where you just have T1, T2, T3, T4, so just 4 parameters, this T5, T6 will be A and B, essentially, if you take some specialization here, because you have a free alphabet X. Anyway, whatever. So if you take this integral, this evaluates very nicely, subject to some balancing condition. Of course, there's always a balancing condition. And if you take X as this kind of, you take this bipartition as just a pair of empty partitions, then you get the elliptic Selberg integral back, which I said here is also due to Rains for some reason, even though I already told you that. Okay. Okay, but that formula I just showed you isn't enough to get the AN version of the integral. You also need some kind of reproducing integral, which looks like I take some density. I'm being very purposely vague here because the formulas, the details are really nasty. But, well, they're not nasty, but they're not nice to write on slides, and I've already punished you enough with some really ugly formulas. So morally, it looks like this. It looks like I integrate a density times 2 kernels, and this equals a single kernel times some stuff. And this allows you to give an inductive proof of the elliptic AN Selberg integral. So you can do induction on the rank. And I should also say that morally, this is how Varna proves the ordinary AN Selberg integral. It's just that the kind of master identity, the AN Cauchy type identities, are proved inductively in a similar way. And one other thing is that actually this edge density I showed you, doesn't come out of nowhere, so to say. It actually is just a special case of this kernel when C equals PQ over T to the 1/2. Then this kernel is actually really only equal to that edge density product I had. So that's where it comes from. Okay. And so Eric came up with this kernel to prove a whole bunch of things. So integral transformations, I said before, for elliptic hypergeometric integrals, to compute branching coefficients, for McDonald polynomials, you can use it for that. There's a paper of Chulhee Lee, Eric Rains, and Olivana. And then you can also use it to evaluate vanishing integrals. So vanishing integrals which are related to Littlewood type identities. So there's all this kind of nice mathematics behind this kernel. And he has variations of it as well. So there's also there's a what he calls a Littlewood kernel and things like this, which kind of do slightly different things than the full kernel. But anyway, I want to say that kind of we also used the same idea in our paper on the AFLT type Selberg integrals, where we used what we called a complex Schur function, which was introduced by Kidell in the 90s, or the 2000 even, I think. And this complex Schur function is really, it's the same, morally, it's the same thing. You take the Schur function, and rather than plugging in a partition in the index, you plug in a sequence of complex numbers. And we used this to kind of prove some kind of AN Selberg integral in gamma equals 1 modulo. So you have to make it a contour integral because you need everything to converge. And as I said, real domain of integration are badly behaved for these AN integrals. But anyway, so you get this complex Schur function object, and this satisfies some nice kind of things like this elliptic interpolation kernel does. But kind of in the middle, we don't know what would do this at the McDonald level for the non-elliptic AN Selberg integral and away from gamma equals 1. Okay. And that's all I wanted to say. I'm sorry if that was a bit quick, but anyway, thank you very much.
Okay, thank you very much. Questions? Sagar, do you
I
have?
had a question. Sorry, were you saying something, Gaurav?
No, I was asking, you were unmuted, so that's why you had a question.
So, when here you considered the classical root systems, what if I was to look at affine root systems and consider elliptic integrals over that? I mean, has that been observed before?
I'm not sure. Maybe Fatchenko and someone else has done this, but I have no idea.
Okay.
Yeah.
And here the root systems that you considered were reduced root systems.
No. So these higher rank Selberg integrals only exist for type A at the moment. There's no in type B, C, and D. People have done very, very small ranks, but this is really just the Selberg integral. There's not much more going on there than that. So
okay. No, I mean that the root systems that you considered. I mean the way things were defined were by the Katha matrix, right? So the Katha matrix over here could be something which is coming from a non-reduced root system for AN type as well. I mean.
Sorry?
I mean, I was just thinking whether an analog of this can be found for the non-reduced root systems as well. But I think, I mean, the whole theory over here requires things to be working over C, right? I mean, the integrals are defined to be line integrals and everything which are going over C. For a non-reduced root system, you'll have to be over
I don't know. Really, the root system here is giving you a kind of a structure of some thing, telling you how to, it's kind of giving you a dictionary of how to read off and how to do stuff with these, how to write out the integral. rather than kind of giving you explicit what so the domain and things like that. But yeah.
Thank you.
Yeah, thanks.
Hi, Seamus. Lovely talk. Just a question about this contour, as in from going from elliptic to the other one, you were still thinking about, or did I miss it? Or there was a way to go to the previous work of yours?
The from the elliptic level to the
Yeah.
classical stuff, yeah. So no, at this point, no. So the connection is not so obvious. So we tried really for a long time to try and do this, but I think that one needs to do it's if you want to take a limit of this elliptic Selberg integral, AN Selberg integral, and get something kind of classical Selberg type, classical AN Selberg type, you really need to do a lot of work. So something naive won't work. And yeah, so that was essentially my conclusion. That's a very vague thing to say, I know, but yeah, we really tried a lot of kind of elementary things, because if when you go from the elliptic Selberg integral, there's a really actually you can obtain a nice kind of Q analog, kind of a Q integral, but not as a discrete sum, but as a contour integral, really nicely from the elliptic Selberg integral. And we do this in that AFLT paper. So the first paper from a few years ago. But
I'll have it.
yeah, but for the general case, we couldn't figure out the details. So I should say that the right-hand side, the evaluation of that elliptic Selberg integral, you can obtain the evaluation of the ordinary AN Selberg integral from it by taking this limit. It's just the integral is well behaved. So analytically, it's dubious. But for the evaluation, if you take this limit, everything it very nicely produces exactly what you want.
Okay.
So there's no relation with the Aomoto type of extensions, you're saying, or that's
Well, yeah. So the Aomoto integral is just you can think about it as just the putting in an elementary symmetric function in the integrand of the Selberg integral, but he doesn't just have this, right? He has some more general kind of thing, kind of formulas like this. But what is called the Aomoto integral is really kind of a special case of this Cadell integral with a Jack polynomial. So yeah.
All right. Any further comments or queries? Okay, then let's thank the speaker. You can unmute yourself maybe.